One large agent handling a request end-to-end costs around $12. Break that same request across specialized sub-agents, and it drops to 40 cents. That gap is real, and it's exactly why teams are building agents that spawn other agents. But most who try it end up spending more than they started with. Here's the tension: spawning sub-agents adds 200 to 500 milliseconds of orchestration overhead per layer. On simple queries, that overhead erases the savings entirely. So why does it work at scale, and when does it quietly wreck you? Think of a senior engineer breaking a sprint into tasks. They don't rewrite code for each junior, they write parameterized task descriptions, assign specific libraries, and set guardrails. If a junior produces garbage output, the senior re-explains instead of doing it themselves. That's exactly what agent spawning is at a mechanical level. A parent agent outputs structured text, system prompts, tool definitions, parameter schemas, and a framework parses that text and boots a child agent with exactly those specs. No magic. Just LLM output becoming executable configuration. In a real data pipeline, the Orchestrator agent outputs a JSON schema defining tool calls, a specialized prompt for a data validator sub-agent, and memory constraints. The framework reads that JSON and the validator agent runs, configured entirely by the parent's text output. Prompt parameterization is what makes this scale. The parent injects task-specific variables into a template, dataset_ID, schema constraints, error thresholds, creating a unique instruction set for each child without any retraining. One template, 3 datasets, 3 child agents instantiated in parallel. Tool binding is the parent's way of enforcing guardrails. A code review agent spawning a static analysis child grants it access to AST parsing, linting, and security scan APIs, but explicitly withholds deployment and file write tools. The child can't exceed its mandate because the capability list is set at instantiation. When a child agent fails, rate limited, timed out, bad output, the parent handles it without the child ever knowing. A data cleaning agent hits an API rate limit. The parent detects the error in the response, waits 30 seconds, and respawns the same agent with identical config. The child is just recreated. Output validation closes the loop. The parent specifies a strict JSON schema, decision, confidence score, reason string. If the child returns freeform prose instead, the parent detects the mismatch, sends the child its own output alongside the schema, and asks it to reformat. That repair happens inside the loop, not in a human's inbox. Here's where teams get burned. Every spawn is a full LLM forward pass, tool binding, memory setup, and state initialization, not free text generation. Spawn 50 agents to parallelize a task and you've paid 50x inference cost plus orchestration overhead. A misconfigured parent spawning 100 children per request, each doing redundant API calls, can burn a monthly budget in hours. And for simple queries, the orchestration delay alone makes the whole system slower than one agent doing everything. The real decision every team faces: sequential execution costs $12 and takes 45 seconds, but is predictable. Parallel sub-agents cost 40 cents and take 8 seconds, but only when the task genuinely decomposes and depth limits are enforced. Neither option dominates universally. Token budgeting across agent layers is the engineering discipline most teams skip. A parent planning to spawn 10 sub-agents must allocate token budget per child and track cumulative spend. If one child consumes 75,000 tokens against the 50,000 allocation, the parent must explicitly decide: abort that branch, queue remaining children, or fail the job. That negotiation is your code's responsibility. Cross-agent state threading is how parallel children stay coordinated without talking to each other. A fraud detector and a compliance checker both read the same transaction record from a shared state object, run independent checks, and write results under different keys. The parent reads both entries and aggregates. Children never touch each other's data. Dynamic agent type selection is what makes the economics work at volume. A request router receives 1,000 simple queries and 10 complex ones. It spawns light agent instances, faster, cheaper, for the bulk, and heavy agent instances for edge cases. Same parent logic, 2 child templates, selected at runtime based on task characteristics. Recursive context windowing is the silent tax of deep agent trees. A workflow agent spawns a task planner that spawns 3 execution agents. Each level summarizes its reasoning before passing context down, turning a 40,000 token full trace into a 2,000 token summary. You fit within the context window, but you've lost fidelity at every compression step. Agent spawning done right cuts latency from 45 seconds to 8 seconds and drops costs by 70%, while improving reliability. Done wrong, it's a runaway process that hemorrhages money with worse performance than a single agent ever had. The difference is explicit budget limits, depth caps, schema enforcement, and knowing which tasks actually decompose. Agent spawning isn't a feature you toggle on, it's an architecture you design with explicit budgets, depth limits, schema contracts, and failure handling at every layer. Get those right, and you unlock real cost and speed gains. Skip any one of them, and you've built a very expensive, very fast way to fail. If this changed how you think about multi-agent systems, subscribe. More systems breakdowns like this every week.